Okay, so thank you very much for the invitation. And today I want to talk about two aspects of the double copy that I've been looking at in the last year with various different collaborators. And one is the brst formulation of the double copy, and the other is more recent work on the direct construction of symmetry transformations via the double copy and relation to asymptotic symmetries. So these two might seem quite different at a first glance, but as I'll try to show you, they kind of go towards the same goal, and we even have some hope that lessons we learn from one can be fed back into the other one. So what is the goal? What is the setup for what we're trying to achieve? So we've seen, you know, in many wonderful talks at this conference already that there's a lot of great results in building the double copy for on-shell objects, and for physical observables. So it's a natural question to ask, is it possible to construct the full space of a gravity theory without looking at special gauge choices, without making special coordinate choices? So basically, how far can we go in trying to build an off-shell description of the double copy? So we're seeking a dictionary which continues to hold when we perform gauge and coordinate transformations, basically. I'll be working in the minimal setup, so just a simple product of two Yang-Mills gauge fields, giving, as we all know by now, the graviton two form and the dilaton. And now what I want to emphasize is that if we can construct the full theory for these three fields with arbitrary boundary conditions and i.e. sources, it should be possible to easily extract the pure gravity theory from here by setting the other two to 0. So first of all, let me tell you a little bit about the brst formulation of the double copy and why we like working in this framework. So even when we don't look at quantum effects, of course, brst was formulated initially for the purpose of path integral quantization, and at the simplest level, just imagine taking the gauge parameters of a symmetry and replacing them with ghost fields. And I'll show you that even if we look at classical off-shell objects, it's quite beneficial to work in this formulation for a number of reasons. So one is that it gives us a very nice gauge mapping algorithm between Yang-Mills and gravity. The other is that it gives us an elegant way to disentangle the graviton and dilaton, which is quite general. And thirdly, it's quite helpful for the construction of a double copy Lagrangians, due to the new color kinematic rules it gives us in the ghost sector of the brst Lagrangians. And I have to say, this was already conjectured by Siegel quite some time ago based on ideas from string theory. So let me just give you a flashing introduction in case you haven't seen the brst formulation before. All we will need for now from here is the following. So to write your brst Lagrangian, you simply start with just a standard Lagrangian, like usual classical Lagrangian for any theory which might have a gauge symmetry, such as Yang-Mills or gravity. You add a gauge fixing term, which we call GF, via Lagrange multiplier. This, of course, breaks your gauge symmetry, but you can restore a global brst symmetry, which I'm giving here at the bottom of the slide, but at the cost of introducing new ghosts. And two things I want to emphasize here. One is, unlike in the standard formulations that you might see in textbooks, we have chosen to couple sources to the ghost fields, and this you can do in a careful way, such as to preserve the brst symmetries. And the second thing I want to emphasize, so when we look, these are just the transformations at linear level for the theories of interest. For the fields, is as advertised, they look just like the usual gauge transformation. So this is just the linearized gauge and diffuse, for example, where the parameter has been promoted to a ghost. But the interesting thing to look at is that this anti-ghost field, which appears in our brst theory, its transformation is actually proportional to the gauge fixing function. So information about the gauge fixing is already encoded inside these transformation rules. So, okay, so having done this, we are now ready to give a dictionary as promised, and this we have already known for a couple of years now, that you can give quite a nice and simple dictionary, at least at linear level, for the graviton two form and dilaton. And the interesting thing to note here is the appearance of this ghost singlet in the definition of the dilaton, and if you want to, in the definition of the graviton itself. You can choose this A to be 0 if you wanted to. And just a quick notation, by this circle, I'm denoting a double convolution of Young-Mills fields together with the bi-adjoint, which is just the zeroth copy in the double copy, basically. And the convolution has some nice properties which allow me to get the symmetries as needed from this dictionary. So now, as promised, let me show you the first benefit of working in the BRST formulation is that we get a nice algorithm for mapping gauge choices on the Young-Mills side to those on the gravity side. So let me just do it for a simple example, but it can be done more generally. So let me start with the most standard, just Lorentz gauge on the Young-Mills side, and let me pick this simple dictionary choice for my dictionary. So by hitting this H-mu dictionary with a BRST transformation, which I have shown you just 2 slides before, I can immediately read off a ghost dictionary. So basically I know what Q acting on H-mu is, and I know what Q acting on each of these entries is, and it allows me to immediately read the dictionary for the ghost field. Then I can conjugate and get the dictionary for the anti-ghost. Now, as I've shown you in the previous slide, Q acting on the anti-ghost is actually proportional to the gauge fixing functional. So I know that this is what I should be getting. But on the other hand, from the dictionary itself, knowing what the transformation rules for the Young-Mills fields and ghosts are, I can explicitly say what Q on C bar is. And then inverting this dictionary that I've shown you here, I can immediately read off what the gauge fixing on the gravity side should be. So it's a very nice and sort of, I'm calling it an algorithm. It's a very nice, like step-by-step way where you don't need to make any guesses. You don't need to look at your final theory and try to guess what the gauge fixing was, etc. So this was at linear level. The second kind of benefit I wanted to show you, and I want to illustrate this with an example that's of quite a lot of interest to the double copy community, and it refers to this JNW family of solutions. So this is some work from earlier this year with Andres and Chris, and this solution has been studied quite a lot in the double copy, both in perturbatively and non-perturbatively. But what we will be interested in is trying to see exactly how to get the full family. So you see here, again, writing at linear level, I'm writing the trace reversed graviton and the dilaton solutions for this family. And the important thing to note is that it's characterized by 2 arbitrary parameters, M and Y. So the question we wanted to ask, and something which hadn't been adequately addressed in the literature up until then, is what is the Young-Mills origin of both of these parameters? And we found that the BRST formulation has a very nice way of giving you this. So, and it also teaches you some new lessons. Good. So the first thing we needed to do was to find the appropriate dictionary. So we know that on the Young-Mills side, we're going to want a Young-Mills solution, which is in Lorentz gauge. So we made use of this gauge mapping algorithm to find, so you can kind of reverse it to find what the ideal dictionary would be, which maps you from some gauge choice to another gauge choice. But the subtlety to note here is that this algorithm I'm giving you is for the construction of Lagrangian. So this is just some arbitrary gauge fixing functional, whereas for the construction of solution, one wants to really impose these gauge choices on certain solutions. And then we found that this is the dictionary that you need, which really takes you from Young-Mills solutions that really satisfy the Lorentz gauge to gravity solutions that really satisfy the Donder gauge. So finally, just to show you quickly, you pick a family of Young-Mills fields described by this parameter alpha. And in addition to this, in the BRST formulation, you pick a family of ghost and anti-ghost fields described by these parameters D and D bar. And here you remember we note the importance of what I was saying earlier, that we have allowed ourselves to couple sources to our ghost fields. So these guys will have some source at the origin, and finally we pick some solutions for the bi-adjoint. Plugging these guys into our dictionary, we find some simple expression for the graviton and dilaton, where now I can give you a nice map between the M parameter. So remember again, the M parameter of the graviton and the Y parameter of the dilaton. So as expected, the M parameter of the graviton can very nicely be mapped to just the contraction of these alpha parameters for the Young-Mills. But for the dilaton itself, you see it's a combination the alpha contractions and the contraction of the D and D bar coming from the ghosts. So in particular, if I wanted to restrict to a Schwarzschild solution, I could very easily do this by choosing these D and D bar appropriately, and note that in doing this, I haven't constrained my gauge fields at all. So I've only constrained my ghost. So as I was saying, this seems like a nice way to construct a pure gravity solutions or actions from the double copy, and this is what we looked at. This is some work with Laurent from earlier this year. So we wanted to see going up to cubic order, does this still hold? Is it possible to have a nice construction of the full Einstein-Hilbert Lagrangian only for gravity from this dictionary that we're proposing? So remember, now we start again with a simple dictionary without any non-local terms. And first thing I want to do is I want to truncate to the pure gravity sector. So of course, getting rid of the two form is always trivial. You just pick your two sectors to be identical. Then getting rid of the dilaton is just a slight generalization of what I was showing you on the previous slide. So I simply pick this contraction of the ghost and anti-ghost to be proportional to this trace over the convolution of gauge fields is exactly such a way that I'm killing phi. So again, I want to emphasize we haven't constrained the gauge fields themselves, and this leaves us with some very simplified dictionaries. So we've done this, we've done the truncation at linear level. So now let's move on to the cubic order. So this is just the standard Yang-Mills BRST action at cubic order. This is the classical part of the action. Here we've eliminated the Lautrup field, the Lagrange multiplier. So now you just see a product of the gauge fixing functionals, and finally this is the ghost sector. So now the interesting part is when we now write this in momentum space, this like kind of emphasize the color kinematic structure at cubic order, we see the first generalization. So we see this first term here, which corresponds to the three gluon sort of interaction, is the one that is very familiar, I think, to everyone in this audience, and is just the usual kinematic factor. But you see what BRST gives you, it gives you a second term here, which corresponds to an interaction of a ghost and a gauge field and an anti-ghost. And I use the notation here, alpha is just some sp2 index, so you just think of C1 as the ghost and C2 as the anti-ghost, just to package them nicely. So what we have is a second kinematic numerator corresponding to the ghost anti-ghost gluon sector. So now we're ready to take the double copy, and in doing so we have to now basically take all the possible combinations, right? So the gluon term with itself will give you this kind of term. Then when mixed with the ghost term, will give you these cross terms, which are the ghosts, and then the ghost gluon with itself will give you this final terms. So here I've abandoned the indices on the ghost and anti-ghost, and I'm again writing them more simply as just the ghost and the anti-ghost. So now we get to make use of the simple linearized convolution dictionary. We plug it in, and we get this action at cubic order. Now, you might, if you're familiar with GR and perturbation theory, you might notice this is not exactly the Einstein-Hilbert action. And this is something that pretty much always happens when we're trying to build off-shelf quantities, is that the double copy will not necessarily land you on the traditional description of that object, but you need to find some field redefinition to map it. But the nice thing in the BRST formulation is that we found a unique local. I'm ignoring, by the way, the ghost sector here. I'm only looking at the field part. So if you were wondering about that, so we found that there is a. Thank you. So we found that there's a unique local field redefinition that maps you between this Lagrangian and the usual Einstein-Hilbert one. And we've also found the gauge fixing functional at second order. And since then, there's been some interesting work of Laurent and collaborators. I think he'll be talking about it tomorrow, where they show that in general, you can find local, it should always be possible in the BRST framework to find local field redefinitions. Of course, this is important for the correspondence at loop level. And there have been other constructions for Lagrangians based on the convolution dictionary, and then going to higher orders in perturbation theory. So now let me just take stock of what I've shown you so far. So the point was that BRST gave us a nice map of shell. It gives us more control over the gauge choices. but we still needed to do some field redefinitions. And these were simplified a bit by the presence of the ghosts, but they are still there. And I believe some of the reason why we always have to deal with these field redefinitions is because we don't have a proper understanding of how to double copy the transformation rules beyond linear order. So remember those nice maps that I was giving you for the ghost fields, they were at linear order, but beyond that, we're just always constructing the, for example, the action directly. So this was one motivation for the next part that I wanted to show you quickly. Another was to understand the asymptotic symmetries from the double copy. And there's been a lot of very recent interest in this. So we thought it would be nice to understand it in various contexts. So we thought it was be nice to understand it at the level of the symmetries themselves. And as a further simplification, as a first step, we looked at the self-dual sector. So here we know, of course, that the kinematic algebra was understood quite some time ago, and we know that the equations of motion double copy nicely, but we wanted to ask a slightly different question, which is kind of in the spirit of what I was showing you earlier, like looking at the transformation rules of the fields themselves and how they double copy. So just very quickly, first we're looking in the bulk, we're looking at the self-dual theory. So we've introduced some coordinates. So these are just the usual light cone coordinates. We split them into some X and Y subsets. So this is the metric in terms of these. We define some epsilons on this space. So all of this is kind of technical, you don't need to worry, but the main thing to take home is that in this language, we find very nice sort of covariant-like ways of expressing the gauge field and the graviton. And these are exact expressions now. And we can see very nicely how for the equation of motion itself, the double copy works very straightforwardly here. But as I said, what we were interested in were the symmetries. So we actually found two families of symmetries. So the first family of residual symmetries preserving the self-duality condition can be written in the following way on the Yang-Mills and the gravity fields. And you see that the parameters are dependent on a subset of the coordinates. And looking at these symmetries just in this form that they are, is not obvious how you would get a double copy from one to the other. So after staring at it for quite a bit, we realized that what one needs to do is, instead of trying to map from the Yang-Mills parameter to the gravity parameter, one should repackage the gravity parameter into this thing that we call the Hamiltonian. Basically, with respect to the Poisson bracket, it acts a little bit as a Hamiltonian, but for symmetries. And then we can repackage the transformation rules, writing them in terms of the scalars. So now, remember, these are actually exact symmetries. And now we find some very simple replacement rules for these exact symmetries. And then looking at the asymptotic version of this to see what they're related to, we find that for this family, again, just going to Bondi coordinates, this is just the expression of the metric, we've obtained a subset of the supertranslation. So in general, this is just the supertranslation vector and how it acts on the metric at null infinity. And in general, f is an arbitrary function of z and z bar. We found a subset of that coming from an antiholomorphic Yang-Mills parameter. Now, very quickly, because I'm running out of time, but I wanted to show you, we found the second family of symmetries that preserve the self-duality condition. So you see the diffeo, so this is just an action on the metric. The diffeo parameter is a little bit uglier in this case. Again, we defined a Hamiltonian, and then we tried rewriting this in terms of the Hamiltonian. Now, this looks a little bit funny. So this looks non-local here, but in fact, it's secretly local. It's just a repackaging that makes it look non-local. So at this stage, this looks like quite a strange symmetry. And we said, but if you use exactly the same replacement rules as before, but now going towards Yang-Mills, we find this transformation rule for the self-dual Yang-Mills scalar, which actually worried us a little bit when we first saw it, but this turns out to actually be a symmetry of the Yang-Mills self-dual equation. So this was a very nice check that made us more confident in these replacement rules, and in particular in this, doing this sort of repackaging is the right thing to do when looking at symmetries. So again, this, just to emphasize, these were done non-perturbatively, the first family, and the second family, we've only looked up to second order so far. So we're still continuing with that calculation, but very quickly to show you the asymptotics of this second family. So we found that here we can get anti-holomorphic superrotations. So generally this vector field for superrotations would have a complex conjugate, but in our case, we just get the antiholomorphic part with this particular, so it's just antiholomorphic, and it comes from a Young-Mills transformation, which for those of you who are familiar with asymptotics might look a bit funny in the sense that it starts at order 1 in R, but we believe it could be connected with this large gauge symmetry related to some subleading soft theorems studied a few years ago by Miguel and Alok. So these were the asymptotic symmetries, and now maybe I will conclude with some future work. So first of all, on the asymptotic side, we believe that putting together the self-dual, so as I've shown you, we've gotten a subset of the symmetries so far, but because of the restrictions that already exist on the parameters at null infinity, we believe that putting together the self-dual and anti-self-dual sector, that will already cover quite a lot of the full set of symmetries, and then we'll be looking into how to extend to the full family of symmetries. And more generally, going back to what I was saying earlier, I believe that having a nice map for constructing symmetries could help you with the stuff I was talking about before, for example, in the construction of Lagrangians or equations of motion. It might give you a quicker way to see what field redefinitions are needed, for example, because these are much simpler expressions than looking at an entire action. And this is how it ties back to what I was saying, but maybe I should finish as I'm running out of time. So thank you.
Awesome, thank you, Silvia. All right, so we have a couple minutes for questions. Carlo.
Yeah, hi Silvia, thanks very much for the nice talk. Could you explain a little bit better if these replacements rule that you find work also at the level of the solution space or just at the level of the symmetries?
Oh, good question. So these, you mean these ones?
I mean, you identify, yeah, a relation between the parameters, right? That generate the symmetries. So I was wondering about the solution space. If you basically, if asymptotically flat solutions get mapped to asymptotically charged less, so to say, stuff in the Yang-Mills side.
Yes, so this is a very good question. We haven't looked at solutions explicitly, but at least for this first step that we've done, which is in the self-dual sector, here we know that you see these equations of motions, they double copy very nicely. So even though I haven't looked at it explicitly, I would say that probably at least for this subset, you will get it for the solutions as well.
I see, thanks.
Okay, Cynthia was next.
I have two questions. The first one is just what do you think the hope is for being able to do this at the full nonlinear level? And then the second question is, do you think that there might be a nice relationship between the asymptotic symmetry story that you're building and asymptotic symmetries as they're studied, for example, in Kerr CFT?
Good. So sorry, the first question, which bit were you referring to exactly to be built at the full nonlinear?
Actually, I'd be interested in just in general what the status is of the full nonlinear level.
You mean for the symmetries?
Not just for the symmetries, for the earlier part too, but I'd love to hear about either.
Good. So do you mean non-perturbatively or just even perturbatively and going to higher orders?
I was thinking perturbatively, but non-perturbatively is also a good question.
Yeah, so for the on the non-perturbative side, I think for now this you could try to understand only in very particular contexts. So for example, these replacement rules that I was showing here, these are actually non-perturbative. Right. So for the construction of actions that I was showing you on the BRST side, in principle, one could continue this construction to higher orders. These field redefinitions and replacements, they might get a little bit uglier as you go to higher, but in principle, I think Leron will be talking about this a bit. Tomorrow you can go to higher orders, and in general, they should, at least in principle, always be possible to do them. So going back to the symmetry story, the reason why I was trying to understand how to double copy the symmetries is because I think the reason why we need the field redefinitions is because the symmetries in general do not copy exactly. And I think there still needs to be a bit of work to be done. But at the general level, I would say that we don't have an answer yet, but we realize that starting from in these particular cases where you know the theory is simpler, we can get some nice results. And for your second question, can you remind me?
The second question was just asking if you think there might be a relationship between the asymptotic symmetry story that you're building here and the asymptotic symmetry story as it's used in the Kerr CFT.
Yes, that would be a very interesting. Yes, we haven't yet. We haven't started looking at any of that, but that would be yeah. Maybe we can discuss some more later. I'm not super familiar, but yeah, that would be an interesting thing to. Yeah, we've only just started exploring this in the asymptotic sector, and we are looking for ways where it could be useful. So that would be definitely something to check more.
Okay, sounds good. Thank you.
Okay, Mal, if you have a quick question, we can hear it now, and if it starts going too long, we can move it on to the Slack.
Just have a quick question. The BRST off-shelf double copy, can you put the 4-point correlator in the BCJ satisfying form just by writing down the ansatz and swapping terms around diagrams?
Yeah, so for the 4-point, I wouldn't know what to say, because what I've looked at explicitly has been just the 3-point in the action that I've looked at. Yeah.
Thanks.